All right, hello and welcome back. A little bit off schedule, but we're back with talking about physics today. So as you can tell by the title, we're going to be continuing our discussion of energy that we began last week. So without further ado, let's jump into it. So the title of today's presentation is More Energy, and the essence of today's lesson is we're going to build upon the conservation of energy equation we developed last week, where we had the sum of kinetic energy and potential energy at the initial point in time is equal to the sum of potential energy and kinetic energy at the final point in time. We're going to basically add just one term to that equation, and with that one term, we're going to be able to solve a lot more problems. So, I alluded to this in the intro of the last lesson, but there is a great relation between work and energy, and this is our expanded work-energy theorem, where work is equal to the change in kinetic energy plus the change in potential energy. So obviously when we go from some initial point to some starting point and we do some sort of movement, we change around a little bit, these quantities will most likely change, which means this work quantity will be non-zero, but this is the very important equation that relates both work and energy. And when we use this equation, we have positive values, which indicate work coming into a system, and negative values are used for work leaving a system. So that's how we use this equation. Now, before we proceed further, we have to define a couple of things, and these relate to forces. Because remember, work relates to forces. If we remember, work is equal to some force times the distance the force is applied times cosine of the angle between the force vector and the direction of motion. That's our equation. So there is this relationship between work and force. So there's two types of forces we want to define. First is something called conservative forces. And these are forces for which the work done depends only on the start and end points of motion, and that does not depend on the path taken. So for example, we consider the gravitational force. On the other hand, we have non-conservative forces, and these are forces for which the work does depend on the path taken. So for example, if we take friction, the work done by friction does depend on the length of the path taken. So these are two definitions that we want to keep in mind, and they might be a little hard to understand at first, but I encourage you to take some time to maybe research it a little bit further. But actually, much of our focus with work and energy is going to be on non-conservative forces, things like friction. So we're going back to work and discussing some formulas with it, and with these formulas, we're going to derive a really neat equation. So I've color-coded a lot of things, but I'm still going to walk you through it. So we'll break work into two components, a conservative and non-conservative component, right? Because we said that forces are either conservative or non-conservative, and since work depends on forces, we'll just separate them. We'll separate work into the sum of conservative forces and non-conservative forces, right? So that would be this equation right here. And remember that work from conservative forces comes from a loss of potential energy. So work conservative is equal to negative the change in potential energy. So this is just by definition, something to remember. But also by definition, we know that the net work is equal to the change in kinetic energy. This is from a couple weeks ago. This is the net work done. So that's the blue thingy here. So we're going to make the substitution where we see work net, we're going to substitute these in, and we'll put delta KE in there. So we get work non-conservative plus work conservative equals the change in kinetic energy. And so just rearranging this equation, work non-conservative is equal to change in kinetic energy minus work conservative. And well, we set up here, this work that's done by conservative forces is equal to negative the change in potential energy. So if we substitute this in here, we get work non-conservative equals the sum of kinetic energy and potential energy, which is basically what we said here. So perhaps I should have specified that this is work non-conservative. So now we've fully defined this properly. So yeah, we have an equation now for work of non-conservative forces. But we can do things, a little bit further. If we know this is our equation, we can, break apart these deltas to subtract the final points and initial points. So we have work non-conservative equals kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And if we just rearrange these terms, get this minus sign and bring it to the other side to make it positive, same thing here, we get kinetic energy initial plus potential energy initial plus work non-conservative equals kinetic energy final plus potential energy final. Now, if I were to just scribble this thing out here and look at the remaining formula, this right here, this looks exactly like the conservation of energy formula we were using previously, right? That's what we're used to. But now we're saying that if there are non-conservative forces present, because in previous examples we didn't really consider anything to do with friction. If you think about our examples from last week and last video, we had like blocks sliding down ramps that were frictionless. We had a roller coaster that was on a frictionless surface, right? There weren't any non-conservative forces. But as we know, in physical systems, it's very common to see these non-conservative forces. So in that case, we can still use conservation of energy. We just have to throw in this term on the left-hand side. So this formula you should be feeling very comfortable with it already because you're accustomed to it. We just have one more term in the left-hand side. And this is our new conservation of energy equation. So whenever we want to solve a problem using conservation of energy, this should be the formula we use. We should not get rid of this term anymore. We're going to use this formula. If it so happens that work non-conservative goes to 0 and we're just left with this, that's great. One less term to worry about. But it's better to start out with this equation than start out with the simpler version of it. So this is going to be the equation that we focus on today. But you might be like, okay, how do we calculate work non-conservative? And it's going to be the same way how we first learned to calculate work, with our equation, force times distance times cosine of theta. And really, if we have multiple non-conservative forces, then it's going to be the sum of all of these forces times distances times cosine of theta. And this is going to be for each force in the non-conservative forces, this set of non-conservative forces. So we would sum them all up. Generally, we just have one non-conservative force, but it is possible to have multiple. So yeah, this is an equation we should also be familiar with, where we calculated work for objects where there were multiple forces. It's just what we're used to. So quick equation recap. This is our new conservation of energy equation, where we see kinetic energy, that's equal to 1/2 mv squared, just like last week. U, potential energy, that is mgh. And work non-conservative, that's going to be F times D times cosine of theta. It's a big equation now. There's a lot of things in it. But as we'll see, it's extremely powerful, and if we're lucky, or if we have good technique, a lot of these terms will end up going to 0. So we're just going to briefly touch on another topic called power and energy, and then we'll dive into some practice problems. So put simply, power is the rate at which work is done. So power is equal to work divided by time, and work we know is F times D times cosine theta, sure, divided by time, but this is actually the equation we'll use in this class, F times D divided by time, and the units are watts, or capital W. And then energy is simply equal to power times time. And this has units kilowatt hours, or kWh. So yeah, that is that. We'll do one problem with this, and but yeah, let's just jump into our questions, and we'll deal with some energy first. So we see a block starts at point A and slides down a frictionless ramp until it reaches the level surface at point B. From B to C, the surface has a coefficient of friction of mu. What is the speed of the block at B? So we were lucky in that I provided you points to break up the movement of this block. You know, we start at A, and then we're going to look at B. The block may not stop at B. It may continue going after B. But we stop at B because that's the end of the frictionless portion of movement. And then B to C, we have this section that's flat and has friction. So we don't want to be mixing friction and frictionless just because there's a lack of consistency there. So if we can break it up, then it's fine. We can totally do that. So we want to find the speed of the block at B, and a friendly reminder is to not forget to define h equals 0. So we can define h equals 0 to be wherever we want. I'm just going to do it at the very bottom. So my h equals 0 line will be right here. And I'll just say this is h equals 0. So from A to B, we can do conservation of energy. So let's just zoom in here. A to B, we use conservation of energy. So we have E initial equals E final, and that tells us, with our new equation, kinetic energy initial plus potential energy initial plus work non-conservative equals kinetic energy final plus potential energy final. So we can do some substitutions here. So the block starts at point A and it starts from rest. So that means it has no kinetic energy initially. Actually, let's just go in here and change these subscripts from zeros and F's. I'll change it to A's and B's, just so that way we're clear on that. So at A, there's 0 kinetic energy. There is some potential energy because the block is not at the h equals 0 line, and we showed last week that the only way for potential energy to be 0 is if the object is at h equals 0. Work non-conservative. So we have to consider throughout the motion of this block as it goes down to B, are there any non-conservative forces present? And, well, no, not really. The only forces really occurring on this block are the force due to gravity and the normal force. There's no friction or anything like that. So actually, we're not going to have any non-conservative forces to deal with. So now let's look at point B. Does the block have kinetic energy at B? Probably, right? It's going down this ramp. It should have some sort of kinetic energy here. What about potential energy? Well, potential energy we know is equal to mgh, and at B we're at h equals 0, so this is also going to go to 0. So that means we're just left with UA equals KEB. And well, we can just use our formula that we know, mgh sub A equals 1/2 mv sub B squared. And we want to find the speed of the block at B, so we're going to solve for v sub B. So how can we do this? We can notice that there's a mass on both sides, so they cancel. And then isolating for VB, we get VB equals 2GHA, or sorry, VB squared equals that, which means VB equals the square root of 2GHA. But we still need to figure out what HA is, and that's simply the vertical distance from h equals 0 at point A. So here we're at A, h0 is here, we're trying to find this height, that would be HA, and we're given that to be H. So we can make that substitution and just say that V at B is equal to the square root of 2GH. And that's our answer for the first part. So that should be a review from last week's lesson, where we didn't have to worry about non-conservative forces. Okay, let's move on. So it's the same question, but now we're asked that mu, so from B to C, the surface has a coefficient of friction of mu, and now mu should be greater than what value for the block to stop before C? Okay, so the block is here, and then it's moving along still because it has some sort of velocity, and we want to see what should mu be such that the block stops right before C. Okay, so now we can see that there is friction involved in this section here. So that is something to keep in mind. And once again, we'll use conservation of energy. So B to C, we'll do conservation of energy. So the energy at B equals the energy at C. So that tells us kinetic energy at B plus the potential energy at B plus work non-conservative equals the kinetic energy at C plus the potential energy at C. And I'm going to bring over our H equals 0 line from the previous slide. Okay, so now let's analyze our equation a little bit. I'll redraw the block here at B because that's where we're starting. So at B, we do have some kinetic energy because, well, in the previous problem, we said that there is kinetic energy at B, and we found it does have a non-zero velocity, so we're good here. Potential energy at B, we said that that's equal to 0 because we're at H equals 0, so that should go to 0. Work non-conservative, we know that we have to have this term now because in this motion, there is a non-conservative force acting on the block, which is friction. So we need to keep this term in still. So now let's look at point C. We want the block to stop right at C, essentially. So if it stops at C, its velocity is 0, which means it has no kinetic energy. So that goes to 0. What about potential energy? Well, once again, if we're at C and B to C is a flat surface, then at C the block is at H equals 0, which means potential energy will also be 0. So that goes to 0. So we're left with kinetic energy at B plus work non-conservative is equal to 0. Okay. So now let's take a moment to think, what are the non-conservative forces acting on the block? Well, first we should think, what are the forces acting on the block, and then we can break it up into conservative and non-conservative. So at B, we have Fg pointing downwards, that's conservative. We have the normal force pointing upwards, that's also conservative. And we have friction opposing motion, and as we said in the beginning, friction is non-conservative. And there's no other forces. So the only non-conservative force would be friction. So let's try to solve for work non-conservative, and then we'll come back to this. So let me just put this in blue. So work non-conservative, that's equal to F times D times cosine of theta. And we said, actually, let me just rewrite this. Changing the color. Okay, here we go. This we said was equal to the sum of F times D times cosine of theta for forces that are non-conservative. But we said that there's only one force that's non-conservative, so that will be just one term, F times D times cosine of theta, and we'll give a subscript of F to the force to indicate that we're talking about friction here. So that would be the non-conservative work term. And, well, we can kind of simplify this further by formula. friction is equal to mu times F sub n, so that times d times cosine of theta. Well, how are we going to find F sub n now? Because we want to solve for mu, we have d, right? That's the distance traveled, so the distance from B to C is x, so we're good on that. Theta, if we remember, is the angle between the force vector and the direction of motion. So if friction opposes motion, theta would be equal to 180 degrees. We kind of still have this Fn term that we have to worry about. So let's try to figure that out. And to do that, we're going to draw a free body diagram. So we're at B here, and then things get, messy, but let's just look right at B. What are the forces involved? And we kind of already talked about this, but we have Fg pointing downwards, we have Fn pointing upwards, and we have friction pointing to the left. Well, we know the block isn't accelerating in the y direction, so the sum of the forces in the y direction equals m times acceleration in the y direction, so that's going to be equal to 0. If we take that sum, we get Fn minus Fg equals 0. So that means Fn equals Fg, and we know Fg is equal to mg. So now we can substitute Fn back into here, and we get this is equal to mu times mg times d times cosine of theta. And it's a lot of variables right now, but it seems like we've simplified it enough. But if we need to simplify it more, that's okay. We'll get to it. So we have this term done. Now we want the kinetic energy, so that way we can, substitute into this equation and solve for mu. That's what we're trying to solve for. So let's do kinetic energy in pink, I suppose. So kinetic energy B, that's going to be equal to 1/2 mvb squared. Well, m is m, it's whatever. Vb, we just solved for in the previous part. That was the square root of 2gh. So let's substitute that back in. We get 1/2 m square root of 2gh squared. So let's just compute this out. We get 1/2 m times 2gh, which is equal to mgh, right? Now let's take a moment to consider that, right? The kinetic energy at B is equal to mgh. Mgh is equal to the potential energy at A. And if we scroll back a little bit, sure enough, UA equals KEB. So everything does check out, so we're in good shape. It's always nice to have that little check. So we have these two terms and we have this equation. We can make a substitution. So we get mgh, let me use the colors, I suppose. mgh plus this color, mu mg d cosine of theta equals 0, and we're trying to solve for mu. Well, let's try to simplify this just a little bit. D is the distance traveled, or the distance the block travels that the force is being applied on. So the force is friction, and that's being applied for a distance of x. So we're going to get rid of this d term and replace it with an x. I'll just use the color black to show that substitution. And then cosine of theta, we said that theta is equal to 180 degrees. So cosine of theta is actually -1. So we're going to get rid of this, and I'll put it in red there. And we're trying to solve for mu. So let's bring this term over to the right-hand side because it's negative, and that'll make it positive. So this gives us mgh is equal to mu mgx. And sure enough, we see the m's cancel, the g's cancel. So we're left with h is equal to mu x And that must mean that mu is equal to h over x. And if you think about it, that's actually kind of interesting, right? The coefficient of friction, such a random quantity, the coefficient of friction depends on two things. First is the height that the block started at in comparison to where it's at now. And second is the distance that friction is being applied for, how long it's being applied for. And you take the quotient of those two terms. It's really interesting to see how that works, that those are the only two quantities it depends on. So x could be, if x is like really, really small here, if the distance between b and c is very, very tiny, the denominator will be really small, which means we need a really big coefficient of friction. And that makes sense, right? Because we want it to stop in a short distance, so the coefficient of friction should be high. Similarly, if x is really, really long, or really big, that means the distance from B to C is like very, very far, so it doesn't really matter what the coefficient of friction is. It can be very small and it'll still stop before C. And then if we look at the height, if we start at a very large height, then that's saying the coefficient of friction should be very high. And that should make sense, right? As the block starts off higher and higher, intuitively it'll have a lot more speed at B, so we would want a high coefficient of friction to slow it down. But if it starts out lower, then its speed at B will be kind of smaller, so we don't need as large of a coefficient of friction. So these qualitative observations about the results that we get are super important that you do. If you happen to take exams for classes and that's why you're learning this material, these are very good multiple choice questions that you can have. Perhaps they provide you the formula and you have to gather some conclusions from it. So it's a good habit to get into, to look at your answer once you're done solving it and see, does this make sense? And in this case, it does, which is great. Wonderful. Let's progress onwards. We're going to move on to part C, which is so similar, except now a block starts at point A and slides down a frictionless ramp until it reaches the level surface at point B. But from B to C, the surface, well, I guess it's not level. The surface has a coefficient of friction of u. So let me just, this should be inclined. So for what value of mu will the block come to rest at C? So same question as part B, except now we're dealing with an incline. And this is going to be a little bit more nasty for many reasons, but again, we can use conservation of energy. I'm just going to add a page because I feel like I'm going to need it. All right, B to C. Let's draw our h equals 0 line. We said that was here. H equals 0. Wonderful. So we'll use conservation of energy again. And you'll notice that I always write conservation of energy when I use it. I just think it's good to indicate to your readers what technique you're using, even though you'll be using a formula. I don't know, I think it's just good practice. So E at B equals E at C. And you'll notice that I'm ignoring A to B. And the reason for that is it's basically the same exact situation as the previous two parts. Like if you consider this diagram here, where we start at H and then we go down to here, this section is identical to this section, which is identical to this section. So we've already handled everything to do with A to B. It's just B to C that's a little messy. So we have our formula for energy. We have kinetic energy at B plus potential energy at B plus work non-conservative throughout equals kinetic energy at C plus potential energy at C. Okay, so what are some things we know? At B, we're at H equals 0, so there's no potential energy there. There is kinetic energy. We've solved for the velocity there. we know there's non-conservative forces present because we go up this friction, or we have this ramp that has friction on it, or the block will be experiencing friction on this ramp, so that's non-zero. Kinetic energy at C, well, we want the block to come to rest at C, so if it's at rest at C, then the kinetic energy at C should be 0. And what about potential energy at C? Well, in the last example, it was 0, but now it's not because we're up here, so there is a vertical distance from h equals 0, and in fact, it's given by y. So this term is not 0. So this is our equation to work with. Let's just rewrite it. Kinetic energy at B plus work non-conservative equals UC. Good. So let's expand that out. 1/2 mvb squared plus the sum of the forces in the non-conservative forces of F times D times cosine of theta equals mghc. So this is the nasty term right here. What are the non-conservative forces present? Well, at B, we have the normal force pointing upwards, gravity pointing downwards, and we have friction, right? Those are the only forces, so it's only going to be friction. And before we proceed, let's actually draw a free body diagram. And we'll do it along the incline from B to C. So it looks something like this, and our block is on it at an incline here, and this is some angle phi. I used to call it phi, but recently I've been hearing a lot of people call it phi, so I'll probably call it phi interchangeably. Phi, fo, fum. All right, what are our forces? Gravity we have pointing downwards, Fg. The normal force is perpendicular to the surface, so that looks something like this. And we have friction, and that opposes motion. If the block is sliding up the ramp, then friction should oppose that direction. So that's also at this angle here, FF. Right, so that's our free body diagram. And it looks like we're going to have to break something up into components because not everything is at right angles with each other. So let's do that. Let's just transfer our arrows over a little bit and just sort of model what it looks like here. So this is Fn, this is Ff, and this is Fg. And we can shift our axes in such a way such that the normal force and the frictional force both are on the axes, but Fg is not. But we know we can break up Fg into its components. So we can have this, which we call Fgy, and this, which we call Fgx. And their vector sum will give us Fg. Right? So now we need to figure out what Fgy and Fgx are. And to do that, we have to utilize this angle phi here. So to do that, let's sort of just bring this Fgx vector here and realize we have a right triangle. This angle here happens to be phi. You can do the geometry to prove that to yourself. But I'll just give that to you to save us a little bit of time. And now if we take the cosine of phi, we get that is equal to adjacent, which is this side, divided by the hypotenuse, which is this. So if we do that, we get Fgy divided by Fg. So that tells us Fgy is equal to Fg cosine phi. And then we can take the sine of phi. And we get sine of phi is equal to opposite over hypotenuse. So sine of phi is equal to Fgx over Fg. And that tells us Fgx is equal to Fg sine of phi. Okay, So we've drawn our free body diagram, we've broken things up into its components, we're in good shape. So let's return to the formula here. Let's get rid of this summation term because we know there's only one non-conservative force. So we have 1/2 mvb squared plus F sub F, because friction is the only non-conservative force present, equals mghc. Right? So we're good there. So we're trying to solve for mu, and we can get mu from FF. So let's break that up into mu times F sub n, d times cosine of theta minus or equals mghc. Right? So we can look at this individually, like each term individually, and perhaps we'll look at this second term here, because we still have this Fn term that we kind of want to get rid of. Everything else in the other equations we either have or we can solve for quite easily. Well, how are we going to get Fn? We can take a look at our free body diagram and see that, okay, this is like the y direction, this is like the x direction, right? So this is y, this is x. And the block is only moving in this x direction. It's not moving in the upwards or downwards direction. It's not flying off the ramp in that way. So the acceleration in the y direction is 0. So acceleration in y direction is 0. So if we take the sum of the forces in the y direction, we should get m times ay. So that'll equal 0. So then what's the sum of the forces in the y direction? If we look here, we have, oh boy, I just saw something. Oh wow, got a raid. Thank you so much for the raid. Very much appreciated. We are talking about physics. So if you're in physics, thank you for the follow. This is wonderful. This is greatly appreciated. I'm seeing a lot of celery. Do you like celery? We're in the mood for science? That is wonderful. No, you're smart. You're perfectly smart. And if you want to learn, stick through it. We're learning about conservation of energy, and we're almost done with this question. We'll move on to another question in just a moment. But thank you for being here. This is wonderful. Yeah, all right, so let's continue on with where we were. And we were summing the forces in the y direction to get the normal force. So in the y direction, we have the normal force pointing in the positive direction. And in the negative direction, we had Fgy. So we're going to subtract Fgy. And remember, that's the y component of the gravitational force. That equals 0. And we're doing this because we want this Fn term, so we can substitute it back in here and solve for mu, right? Well, lucky for us, we solve for Fgy right over here. So we can solve for Fn. This gives us Fn equals Fgy, and that's going to be equal to Fg times cosine of phi. Great. So now we're going to return to this massive equation that we have here, do some substitutions, and solve for mu. And we're going to see that this turns out to be another really great equation. So let's do this. We have 1/2 m velocity of b squared plus mu times Fg cosine theta. Well, we know Fg is equal to m times g. So mg cosine of phi. Let's do that substitution. Mg cosine of phi times d times cosine of theta. And you're like, this is getting too complex. We have phi and theta. And it feels like we're just writing a bunch of Greek and English letters. Like, how is this even physics at this point? And I assure you, it is physics. We're almost there. So there's a lot of things to consider here. But what we'll notice is that from this equation, we have m in every term, so we can cancel those out. That'll help us simplify a little bit. And then we're going to solve for mu. So we get mu g cosine of phi times d times cosine of theta, which is just this term here. And then I'm going to bring this term to the other side. So that's equal to GHC minus 1/2 VB squared. Thank you for the follow, guys. This is greatly appreciated. All right, back to this. Well, the velocity of B we solved for in part A. Thank you again for the follow. So the velocity for B we said was equal to the square root of 2gh. So we can do that substitution. And in fact, I'm going to divide both sides by this term here to isolate for mu. So mu is equal to GHC, which we don't have yet, but we'll solve for it, times 1/2 square root of 2gh squared, right? So this VB, I put this in, and we're squaring it. And now we have to divide by g cosine of phi times d times cosine of theta. And there's still quite a bit of work to do, but let's try to simplify this mess first. So we get mu equals g times hc minus 1/2 2gh. All of this over g cosine phi times d times cosine of theta. All right. What do we have here? We have a 1/2 and a 2. Those cancel. We have a g, another g, and a g here. So those cancel. So this gives us hc minus h over cosine of phi times d times cosine of theta. Right? So now we have to scroll back and figure out what is h sub c, what is d, and these terms, and cosine of theta. So we can probably handle cosine of theta easiest. This cosine of theta, we have to be very careful where it came from. That came all the way from up here when we were solving for work due to friction. And remember, what is theta in the equation for work? Theta is the angle between the direction of motion and the force vector. So in this case, cosine of theta is cosine of 180 degrees. So let's just get rid of theta and write 180 degrees here. Cosine of phi, we can leave that how it is because we're given phi in the problem. D and hc those are the points of interest. So hc is the height at C. So we're at point C here. We're not at h equals 0. We want this vertical height. So that would be y. All right. So that would be h sub c there. And then distance, lowercase d, that is the distance that the force is being applied for. So that would be the distance from B to C. Well, now, how are we going to solve for that? We're at an incline. So this is a little right angle here. And we have a great formula to find this length here. Hopefully you remember Mr. Pythagoras. And Pythagorean theorem says that this side squared plus this side squared will give us this side squared. So this will be equal to the square root of x squared plus y squared. So now we can go back here and do our substitutions. H sub c we said was y minus h, cosine of phi. D we just solved for, square root of x squared plus y squared. And then cosine of 180 is -1. So we can actually bring this -1 into here and change the numerator a little bit. H minus y over cosine of phi times the square root of x squared plus y squared. And that's pretty much the equation that we have. And that's pretty much the answer. And we'll sort of just leave it at that for now. So this is a lot more complex. We can simplify this a little bit more, but I'm not going to worry about that now. But remember from part B when it was a flat surface and we saw that it was just simply the ratio of h over x? This is almost the same thing. We have our h in the numerator, and in fact, we're taking h minus y. So that would be the starting point compared to the ending point. That would be this distance here. So that's a good sign and matches part B. And then we have the square root of this x squared plus y squared. So that does relate to the distance we travel here, and that's in the denominator, so we should be feeling pretty good about that answer. So I know this one was complex, but yeah, it's definitely a great problem, merges everything we've learned thus far. So that's our first problem of today. We'll move on to the second question now. If there's any questions, feel free to leave it in the chat. I assure you this question is a lot easier. It's not going to take us as long. So we have Alice and Bob who throw baseballs of identical mass vertically into the air. Bob releases his baseball at an initial velocity of v, and Alice releases hers at an initial velocity of 2v, and we just want to compare the maximum heights of the two balls. So, as always, we're going to draw a picture, and we are going to see my wonderful skills of art. So we have Bob here, and he has a baseball, and he throws it up with some speed v. And then we have Alice here. I'll just write their names underneath. Give Alice some long hair. She has her baseball, and she throws it up with the speed of 2v. Pretty good drawing. It's so beautiful. I appreciate it. I don't know if you're talking about the math or the art, but probably neither one. Nailed it. Appreciate it. So yeah, this is our drawing. And we can use conservation of energy once again, and we'll see that it can be applied in so many different cases. So we can do it for each ball separately. So the ball for Bob will go up to like here, perhaps. So we want to define our h equals 0 line. So we'll just do that at where they throw the balls. So that will be h equals 0. And then this is just some final height, which we'll call h for now. So for Bob, energy initial equals energy final. So we have our equation that we've been working with. Kinetic energy initial plus potential energy initial plus work non-conservative equals kinetic energy final plus potential energy final. Right? A seemingly complex equation for such a simple problem. Oh, thank you so much. I'm trying my best to explain it to you guys, so I'm glad you're enjoying it. So we'll take a look at what kind of energies are present. So we're only looking at Bob here. Let's not worry about Alice. I forgot to write her name. I'm so sorry, Alice. So initially, we're at this point here, and finally, we're at the highest point. Remember, we're comparing the maximum heights, so we want the maximum height of the ball to be our final point. So initially, there is no potential energy because we're at the point h equals 0. So this goes to 0. Are there any non-conservative forces? Well, let's think about the ball in motion. As it's going through the air, there's only one force being applied to it, and that's the force of gravity, right? The thing that's pulling everything down. There's no other forces. There's no normal force. There's no friction. Sure, you might think air resistance, but we are not going to touch that right now. That's going to be a little bit too complex. So lucky for us, non-conservative work goes to 0 as well. Now we want to consider the final point, when the ball is at its maximum height. And do I have some sort of bouncy ball with me? What do I have? Okay. I have a box of tape here. So we'll pretend this is a ball, right? So I'm going to throw it in the air. And we'll notice that at the very top, at the maximum point, the velocity of the box changes its direction. It goes from going upwards. Yeah, I could use that bouncy ball. I could really use that. But at the maximum point, the velocity changes its direction. It goes from going upwards to going downwards. And when we have a change of direction for velocity, that means the velocity is momentarily zero at its maximum height, right? It sort of makes sense that at the maximum point, the ball is basically at a zero velocity. Exactly. At its top, it's going to be purely potential energy. That's a really good point. And that is true. We're not going to have kinetic energy at the top. And as our commenter mentioned, we do have potential energy. And that's because we're no longer at our h equals 0 baseline. We do have some positive value of h, so we leave that there. Great. So that simplifies our equation a little bit. We have kinetic energy initial equals potential energy at the final position. And now we'll do a little substitution. 1/2 m times the velocity that Bob gives it squared equals mgh, and I'll just denote that as h sub b for h sub Bob. Okay. And so Bob releases his baseball at an initial velocity of v. So actually, we just don't really need the subscript b here. We'll just leave it as v. And then we can solve for h, right? And then we'll solve for Alice's height and compare them. So masses cancel, and then we just have to divide by g on both sides. So we'll get that the height for Bob equals v squared over 2g. Okay? So that's how Bob works. So now let's do Alice, and Alice will be very similar. In fact, what I'm going to do is I'm just going to copy all of this that we wrote up here, and let's just analyze it to make sure that everything holds true. Kinetic energy initial is non-zero. That makes sense because Alice throws the ball upward with some initial velocity. Potential energy is 0 initially. That should be good because we're at the h equals 0 line. There's no non-conservative forces, so that should also be 0. Great. At its maximum point, I guess Alice's will go much higher, so we'll draw hers up here. At its maximum point, there is no kinetic energy, as we discussed with my tossing of the tape, so that goes to 0. And there is potential energy at the end, so good, we can reuse this equation. So again, we have kinetic energy initial equals potential energy final. We have 1/2 mv a squared equals mgha. So now we have to figure out what is v sub a. Well, when it was v sub b, we got rid of the subscript b because we said, oh, it was given to us that the initial velocity is v. You have to know the formulas for working these out and then use the information given. Yeah, in this case, it's very formulaic and using the equations given, but the main thing here is figuring out which sort of formula to use. And we can use a lot of different techniques. We're just choosing to do conservation of energy today because that's the topic of today's lesson. But I'm sure you could use like kinematics in one dimension, and we have a good video on that. But yeah, so getting back to this, v sub a is also given to us. That's 2v. So let's make that substitution in. But first we can realize the masses cancel. So this gives us 1/2 times 2v squared equals g h sub a. And we want to solve for the maximum height. So h sub a equals 1/2 2v squared over g. Let's simplify the numerator a little bit. We have 1/2 4v squared over g. So that gives us 2v squared over g. So now we're asked to compare the maximum heights of the two baseballs. Right, yeah, we do need to know what forces act on the body at any time. That's a really good point. And we mentioned that as the ball is flying through the air, the only force that's being applied to it is the force of gravity. And that's why our non-conservative work went to 0, because there were no non-conservative forces. So let's just do a little comparison. So the height for Bob is equal to v squared over 2g. And for Alice, it's equal to 2v squared over g. Well, Alice, I can rewrite it a little bit and say that this is equal to 4 times v squared over 2g. Right? If we were to do this computation, 4 would cancel with the 2. We would be left with the 2 there. So that would be 2v squared over g. Right? And the reason I did this is because this v squared over 2g is equal to h sub b. So really, if this is h sub a is equal to 4 times h sub b. So that's saying Alice's baseball will go 4 times as high as Bob's baseball because she threw it at twice the initial speed that Bob did. So that's pretty interesting how we see that just 2 times the initial velocity will do a 4 times change in height. And again, we can do this with kinematics, with those equations, but it's very possible to do it with energy, as we just did. Awesome. So we are going to move on to the last question for today. Unfortunately, it has a couple of parts to it, so it's not really the last question. But it's pretty easy to understand. So we had Alice and Bob. Now we have Carlos. So Carlos pulls a 10 kilogram block from rest across a 100 meter level frictionless surface. That should be exciting for us. With a force such that the block accelerates uniformly at 2 meters per second. So let's highlight uniformly, frictionless, maybe underline some of these thingies that could be helpful. The direction of the force is seen in the diagram. Wonderful. The coefficient of friction between the block and the ground is 0.2. And we're asked, what power does Carlos exert on the block? I'm getting imposter syndrome. He was like so quiet. That's funny. That's really funny. I don't think I know any Carloses. I have to think about that. Anyways, so we want to find power. We introduced the equation for power. We said power is equal to force times distance divided by time. That's our equation for power. So we're given distance in the problem. That's 100 meters. So I guess let's just write that here, 100 meters. So we're good on distance. We don't really know the force just yet. We just know that he pulls it with some force, and we don't really know time. So those are kind of the quantities that we want to solve for. So let me just get things set up here. He was a big dude. Oh no. Okay, so how are we going to do this? 2 things we need to solve for. We can solve for force first. And the big thing to take into consideration is what are all of the forces present. So to do that, we will draw our free body diagram. So that dot will represent the block. And what are the forces present? We have gravity pointing downwards. We have the normal force pointing upwards because it's on a surface. To the right, we have the force that Carlos is exerting on the block. So we'll just label that like F sub P for like push or pull. We could do F sub C, but I'm just choosing F sub P. And then there's no friction. So we're good on that side. All right. Great. So we can see that the block is not accelerating. Actually, wait, did I mess this up? I think I messed this up. This should not be frictionless. This should be frictioned. Because we're given a coefficient of friction right here. So that's my bad. Anyways, so that's entirely my bad. Which means that we do have the force of friction in the opposing direction. I was wondering why my work wasn't matching up. Okay, anyways. So the force that we're curious about is the force that Carlos exerts on the block, because we're trying to find his power. So F sub P is what we're trying to solve for. Well, let's just take the sum of the forces in both directions just to be safe. Why not? Let me add a page. All right, so let's take a look in the y direction first. So by Newton's law, the sum of the forces in the y direction equals mass times acceleration in the y direction. So is the block accelerating in the y direction? Boy, I surely hope not, because that would be a really chaotic block just flying up and down all of the time. So certainly it's not accelerating in that direction, so that's going to go to 0. So what is that sum of forces? In the positive direction, we have the normal force. And in the negative direction, we have F sub g. So that's going to be equal to 0. Great. No, don't worry, I like the emotes. It's good. And then we can solve for the normal force or the gravitational force. So we said Fn is equal to Fg, and we know Fg is equal to mg. So we have everything like equal to each other there. We're in good shape. Not entirely sure why we wanted to do that, but it's helpful. Now we'll consider the x direction. So again, the sum of those forces should be the acceleration in the x direction. Well, we're given that the block accelerates uniformly at 2 meters per second squared. So it's not non-zero this time, but we do have the acceleration. So in the x direction, in the positive x direction, we have Fp. And in the negative x direction, we have the frictional force. And that's going to be equal to m times a. And I'll just leave it in terms of variable. We won't do any substitutions yet. Okay. Well, we can break apart f sub f into, well, let's actually just move f sub f to the other side because we're trying to solve for f sub p. Yeah, I'm not sure what went wrong with the timing out, so after the stream, I'll try to fix that. I'll try to remember that. So anyways, f sub p is equal to max plus f sub f. And now we can do our substitution by formulas for f sub f. We get f sub p equals max plus mu times f sub n. And now it becomes clear that, okay, f sub n, it's good that we did this thing on the left-hand side because we know that mg is equal to f sub n. So we can do that substitution again. So we get f sub p equals max plus mu mg. So now, can we solve for f sub p? Do we have all of the quantities? Mass, yes, we're given that. Acceleration, yes, we're given that. Mu, yes, we're given that. Mass, we already said we have that, and g is a constant, so we can solve for f sub p. So that's great. And let's just do that. So this will be equal to 10 times 2.0 plus 0.2 is the coefficient of friction, times 10 times 9.8. Remember, lowercase g is 9.8. If we do this multiplication out, I hope we get 39.6 newtons. Right? So that's the force that Carlos is applying to the block. So that is the force for the numerator. We have the distance, we still need time. So there's still work to be done. Well, how are we going to solve for time? And you might be thinking that, oh, let's use energy because we've been using energy this entire lesson. But if you take a moment to consider what does energy give us, energy usually gives us like height or velocity, height or velocity, and then solving for time could be a little bit challenging. So instead, we can use kinematics because we're traveling in one direction and we have a uniform acceleration. Why not use kinematics? So, what are the known quantities that we have? We know that delta x equals 100 meters. We know acceleration is equal to 2.0 meters per second squared. What else do we know? We're trying to solve for time. Initially, the block is at rest. Whoops. So that means the initial velocity is equal to 0. So we have a lot of quantities. We have to find which kinematic equation to use. And the correct one to use would probably be this one, 1/2 AT squared. Because we're solving for time, and all 3 other variables we have quantities for. So let's solve for time. Delta x is 100. Initial velocity is 0 times t is equal to 1/2 2 times t squared. So this term goes to 0, and we're left with 100 equals 1 times t squared. So t equals 10 seconds. It can't be negative 10 seconds because, well, when we start talking about negative time, things go completely bonkers, and we don't want to worry about that just yet. So now we can finally solve for power. We have this equation here. We solved for force. We solved for we were given distance, and we solved for time. So power is equal to force times distance divided by time. So the force comes from here, 39.6. The distance is 100 meters. So 100, and then we divide that by 10 seconds. And when we do this algebra, we get 392 watts, or 396 watts. And that's our answer for power. So it's kind of hard to conceptualize how much 1 watt is. Like, for a Newton, usually what we consider a Newton to be is like if you were to hold an apple, the force that you feel by the apple is about 1 Newton. A watt, it's much harder to understand. So we can't really tell if he's applying a lot of power or not a lot of power. But we can sort of get a understanding based off of the force he's applying, nearly 40 newtons. Yeah, so that is part A of the question. We're going to move on to the last part of the question, which is, again, asking about power, and it's the same context, same block and everything. The only difference is that now Carlos is pulling it at an angle, so now he's really messing with us. Oh my goodness. So just like before, we started out the problem by drawing this free body diagram. So we'll do the same thing. And we also then proceeded to sum the forces in each direction. Good old Carlos, I agree. He's totally messing with us today. Let me add another page. So let's draw our free body diagram. We have our block here. Gravity stays the same as it should. Normal force stays the same as it should. Friction opposes the motion, so that's good. And now we have this, F sub p, and we'll zoom in here, where this is a 45-degree angle. And, well, as we're accustomed to now, when we have forces at these angles, we like to break it up into their x and y components. So we'll have this pink force vector, so that'll be fpx, and this other pink one will be fpy, and together their vector sum will create fp. Okay, well, let's solve for fpx and fpy. So we can do that by taking, I'm going to try to fix the timing out issues. I'm sorry about that. So we can take the cosine and sine of that angle. So cosine of 45 degrees. We want to take the adjacent side, which is fpx, and divide it by the hypotenuse, which is f sub p. So let's do that. And then we can solve for fpx, just say that that's equal to f sub p cosine of 45 degrees. And then similarly, if we take the sine of 45 degrees, that's the opposite. So that's fpy divided by fp this time. And then again, we can solve for fpy. fp sine of 45 degrees this time. About resistant forces and Bob and Alice's baseball shenanigans. That's funny. Okay, so we've broken up into our components, and now we want to sum the forces in each direction. So we know that the block is not accelerating in the y direction, but it is accelerating in the x direction. So if we sum the forces in the y direction, that should be equal to 0. But if we sum the forces in the x direction, that is going to be some non-zero quantity. As in flying bats, the animals, if they were throwing vertical balls after dusk. Oh, I get it. That's a good one. That's a good play on words. Okay, so let's do it. let's just do it. So in the y direction, we have 3 forces this time. We have the normal force, we have Fpy, and we have Fg. So Fn and Fpy both point in the positive direction. Fg points in the negative direction. That's going to be equal to 0. Okay, not quite sure why we want this just yet. Hopefully it'll make sense in a moment. I'm kind of confused as well. So in the x direction, we have 2 forces. We have Fpx and Ff. So Fpx points positively, Ff points negatively. That's equal to max. Okay, great. So we solve for Fpx, that's equal to Fp cosine of 45, and we're trying to solve for Fp, so this would be a very helpful substitution. Fp cosine of 45 degrees equals max, plus I'm going to move this Ff term to the other side. And actually, let's just make a substitution. Ff, by formula, we know that's equal to mu times Fn, right? And well, I know, I'm sorry, I can't fix it right now. I'll do it after stream, I promise. I promise. Let me write it down off to the side. Fix timing out. Okay. I'll fix it. Okay, so we're trying to solve for Fp, and we have an equation with Fp in it. We just have a lot of other stuff in it. Fn, we can perhaps get from here, so let's try doing that. Fn is equal to Fg minus Fpy, and we know that we have equations for both of these, Mg minus Fp sine of 45 degrees. So making this substitution might be helpful. Let's just try it out. Fp times cosine of 45 degrees equals max plus mu times times mg minus Fp sine of 45 degrees. But also the time of day is therefore variable in the question because there are bats in the air at night, but not during the day. Okay, I see. Have you ever seen a bat before in real life? I've never seen a bat in real life. Like, never in person or like in a zoo or anything like that. They seem kind of frightening to me though. I'm kind of scared of them. Anyways, so back to this equation. We have another Fp term here, and that's what we're trying to solve for. So like, let's try to do this distribution. We get Fp cosine of 45 degrees equals max plus mu mg minus mu Fp sine of 45 degrees. Let's try to put all of these Fp terms on one side. So Fp cosine of 45 degrees plus mu Fp sine of 45 degrees equals max plus mu mg. And now we'll factor out an Fp here. And we get Fp times this quantity here plus mu sine of 45 degrees equals max plus mu mg. And now finally, we can divide both sides by this. Max plus mu mg divided by cosine of 45 degrees plus mu sine of 45 degrees. And we can make all of the substitutions that we want to. Let me just write it out here. This would be 10 times 2 plus 0.2, 10 9.8, all of this divided by cosine of 45 degrees plus 0.2 sine of 45 degrees. And if we compute that out, we get 46.66 newtons. So that is quite a bit more than the 39.6 from before, but that should make sense since he's pulling it at an angle now. So we solve for the force. Remember, we're trying to solve for power. That's equal to force times distance divided by time. We have the distance still. We just found force. Now we want to solve for time. And in fact, if we look back to how we solved time, we just used kinematics. And that didn't really depend on the angle of the force, which is the only thing that's changed. So this time should remain the same. So time equals 10 seconds. So now if we solve for power, power is equal to F times D divided by T. We get 46.66 times 100 divided by 10. This is equal to 466.6 watts. And we can see that 466.6, that is greater than what we got before by about 70 watts. And this should make sense, right? Because in this example, he was pulling it, Carlos was pulling it in its direction of motion. So it slides along better, it's going in that direction of motion. Whereas here, he's pulling it in this direction, but the block is sliding across the floor. So if you were imagine, like you were Carlos, this would require a lot more effort than if you were able to just pull it horizontally like that. So that's why we see that the power here is a lot greater. And that actually concludes our lesson today. So yeah, hopefully you enjoyed that lesson, a continuation of energy and power. So yeah.